So, hello, good afternoon. I'm Brian McCallister, I'm the special guest. And today we want to talk about processing very large event streams at Groupon. Is the mic coming through clearly if I hold it at about this distance? Good. So, there is myself, two coworkers, AJ and Erik Weathers, who actually have all the fun, meaty parts of the presentation. I get to do the setup and sort of talk about the problem because I'm going to start coughing in about 10 minutes. So at Groupon, we have a whole lot of events that we process, be they web logs, mobile logs, application level events, sort of operational metric type events. And if you just talk about ones feeding into the bulk of our storm topologies, which this is going to center around a lot, it's on the order of 100 to 200,000 events per second, sort of nominally throughout the interesting part of the day, which isn't gargantuan, but it's big enough that you have to start doing some interesting things, particularly when you couple it with dozens of different ways of processing this that you want to do, and then sometimes creating new streams out of those streams to feed back in. And so this talk is going to focus on what we have learned in doing this and what we have done to make it work well, sort of developmentally and operationally. And so the starting point for almost all of our stream processing is Storm, which came out of Backtype and Twitter a few years ago. I don't want to go too deeply into how Storm works, so I'm going to do a quick poll. Who here is comfortable with the basic abstractions of Storm? That's not as big a concept. Okay, so I'm going to go into them a little bit more. So Storm works on what it calls a topology. And a topology is made up of spouts which send events into the system. So in our case, the starting source of events is almost always Kafka. So there's something called a Kafka spout that reads out of, actually, hold on, quick show of hands. Who does not know Kafka? Does not know Kafka. Kafka is a high throughput pub sub system that works pretty well. And you can just think about it that way. It's a high throughput pub sub that works pretty well as compared to high throughput pub sub that doesn't work well, which is the bulk of them, including the ones I've written. So spouts feed things into Storm. You then have processors that an event feeds in as what Storm calls a tuple. This is probably because it started its life in Clojure, and Clojure hates types. So everything is a tuple, although it gets complicated now that most people write their stuff in Java or even Ruby within Storm. And conceptually, a bolt does a little bit of processing and then emits more tuples that go to another bolt, that emits more tuples that go to another bolt. So you can start gluing together how you want to process the data, a lot like piping things together in the shell. It's a way of thinking about dealing with streams of data that most developers are pretty familiar with. And you can emit multiple ones. This sort of little tiny topology I have here doesn't really do that. But we will see much more complicated topologies later in the talk. And so the thing that Storm does is it provides a programming model for doing this that's pleasant to work in as a developer. And very importantly, it also assumes that you can't do all of this on one machine because you just have too much data or too much processing. And it provides very good error recovery, error handling mechanisms to replay streams of tuples from points in time to handle failures. That's really the main benefit that Storm brings over something hand-rolled, is that it has some clever things for handling error and recovery in a distributed system, which we're not going to actually go into that except to say that you turn them off when you want high throughput. So from a developer perspective, when you're writing a bolt, it really is, a tuple comes in, you do some stuff, like here, we get a span. This is actually a subset of a topology for processing Zipkin spans. We do some stuff with it, you do some stuff with it, and then you emit another tuple. And you'll just glue together a bunch of these things typically. And this is, going in. So when you actually, oh wow, the colors really don't show up on the projector. This is all colorized, but that's not going to help you. Little too subtle, I apologize. So because we don't want to go into how Storm works to a large degree, from a programmer perspective, we want to talk about how to do it when you've got lots and lots of teams using it, lots and lots of events, and how do you do that reasonably efficiently. It's important to understand the core abstractions that Storm uses, because we're going to talk about them and then we're going to twist them around sideways and put them through a ringer and well, Erik's going to do horrible things to them. So when you look at Storm, there's a few other things like a Zookeeper cluster, because you can't have a distributed system without Zookeeper in 2015. With Nimbus, the Nimbus is conceptually the controller for the whole thing. It sort of assigns, you submit your topology, which is your graph of processing, to the Nimbus, and it puts it out to a bunch of worker nodes. So this is like 3 different servers. Now the worker nodes, have a supervisor running, and this is similar to an Erlang supervisor, but just different enough to be confusing, where a supervisor runs a worker. A worker contains executors, and the workers are separate processes. They're child processes of the supervisor. They start its own JVM. The executor is not a Java executor, despite being in Java. It is a single execution thread and a scheduling thread. And you put tasks for a topology into an executor. You can technically put more than one task on an executor running in a worker, but you don't ever want to do that because it's bad. And if anybody actually knows why you'd ever put more than one task into an executor, find me afterwards and explain it, because I do not understand why it's possible. So a topology then that we saw is split up into a whole bunch of little tasks that work. So if you think about the spout is set up, we run 3 instances of the spout here. Say this is Kafka, we have 3 partitions, so you can actually get 3 simultaneous readers that spew things in. And then you have a stream of stuff going from the spout, pushing into bolt A and bolt X. And you can do various things to say, try and put it on the same machine, but if you can't, put it somewhere else. And it's always 1-to-1. So this will emit a tuple into here. This will emit a tuple into here or into here. And Storm takes care of plumbing the tuples all the way through the system. The worker, takes care of running all the tasks for a topology. And here we have what Storm out of the box approximately looks like trying to run just that one topology. Now we have dozens of topologies, so it gets even more complicated. Which is what the rest of the talk is about. Well, half of the rest of the talk is about. I do want to stop here, though, because I went through the explanation quickly. And I want to say, if you do not understand the different components here, a physical server or virtual machine runs a supervisor. A supervisor runs workers, possibly more than one. A worker runs executors, which run tasks associated with a topology. There's a lot of layers of sort of nesting of control here, and it's going to get murky. So this is your opportunity to ask the questions before it gets murky. I'm way better at explaining than I thought I was if there's no questions. Going once. Going twice. Okay then. So that's the basics of Storm out of the box. Now to talk about how we actually make this work for a large number of teams, a large number of topologies on a slightly smaller set of hardware, we have Erik Weathers, who leads the sort of Storm on Mesos work at Groupon.
So is this working? Yeah, cool. Okay, so as Brian said, we have a ton of different topologies that are running inside of Groupon. And it used to be that individual teams would have to manage their own Storm clusters, gain all the expertise on running Storm, learn about all the different operational aspects. And then we also have inefficiencies where we have underutilized clusters because of general issues with needing to acquire hardware in advance to provision your machines for your clusters. And also that Storm itself doesn't lend itself to efficient utilization of underlying hardware because of the resource scheduling model of Storm, which I'll get into here in a second. So first, I want to introduce the concept of Mesos and how it works in general, and then I'll apply it specifically to our use case of Storm. So if no one's heard of Mesos, or I'll do the survey thing. How many people are familiar with Mesos? So that's actually pretty cool. So I don't have to go into super detail, but basically Mesos does resource scheduling on worker nodes. So given an application framework like Hadoop or Storm or MPI or anything else you can imagine, it might want to run on many different hosts spread across a cluster. And Mesos allows you to schedule your tasks onto these various worker nodes. It has its own mechanisms for maintaining state for the master so that it can be HA. And like two of the core concepts of Mesos that need to be understood for you to really grasp the rest of the talk, my section at least, are the scheduler and the executor. So each framework, Storm, Hadoop, whatever, has a scheduler, which is a thing that Mesos talks to. And it says like, hey, do you want to run anything on Mesos? And the scheduler's like, yes, please, run these tasks. Then Mesos will realize those tasks onto the actual worker slave nodes. And there's different ways of doing it, but the standard way that we also are using in Storm is to run another executor. And this is where we get into a little bit of terminology confusion, because I've talked about tasks and executors here, and Brian also talked about tasks and executors, and these are different things. So again, going back to the Storm model, you have executors and tasks. These are the most low-level things in this whole system. They operate on the individual tuples that are flowing through the system. They might do things like aggregating together two different log lines, whatever you can imagine. And they just run in this threaded model of the executor, the tasks do. Now for Mesos, going back, the executor was the actual controller of everything that's running on a particular slave for your framework. And it's going to run individual processes for your framework as Mesos tasks. So this is kind of the Matryoshka doll, I forget how you said it, but babushka doll is how I know it, of the different layers. So at the outside, you have a worker host. Within that, you have a Storm supervisor, which is actually the Mesos executor. Within that, we have the Storm worker, which is actually the Mesos task process. Then you have the Storm executor, and then the Storm task. So whenever you're talking about tasks and executors with respect to these two different systems, you need to be very clear about which level you're talking. So to bridge together these two different systems, we leveraged an outside, or rather existing open source project for creating a framework on top of Mesos for Storm. It was actually written by the original author of Storm, Nathan Martz. And so we've just run it for a while, unadulterated, and we've recently started making changes to it. So the way it works is that it interfaces between Storm and Mesos by implementing various Java interfaces. And I have, well, I'll get to it in a little bit about exactly how the interfaces work. But the most important thing to understand, really, for thinking about Storm versus Mesos is that they're very different in terms of their resource scheduling. Storm has no knowledge about CPUs and memory and things like that that Mesos knows all about. Because how Mesos works is it looks at a given host and it's like, okay, we have 20 cores, we have 20 gigabytes of RAM available, and it offers that out to the schedulers saying, hey, you guys want to use this? But Storm doesn't know anything about that. All it knows is this concept of a slot, which I'll explain. So imagine this top box is a single host. It has 4 slots, where really all they are is a place where it can store, not store, but run a worker process. Because Storm's Nimbus has these worker processes that are going to do all the processing. It needs to stick them onto nodes. So what it does is it asks the cluster, hey, how many slots do I have available? And it's like, okay, I have 4 from this host, and it's like, okay, I'll just shove some topologies into it. So that's what I represent below, where topology red is in the top left, and then the teal one is on the right with 2 different worker processes in the single host, and there's a third topology on the bottom left. But one of the bad things about this whole model is it's very static. You have, as you set up your Storm cluster, you have to decide how many worker processes you're going to create. You can't make it dynamic to the actual demands of the various topologies you're going to be running within your system. So it's pretty inflexible. And if you're allocating different types of machines, you have to think about, well, this is a much beefier machine. How many slots does this really represent? So we'd prefer to have a model that instead takes into account the actual real resources within the slave nodes and allows us to schedule what the actual topologies need. The other thing I'll reference is that when you're running inside of a standard Storm cluster, you have no real incentive to think about how many CPUs or how much memory do I need per worker process. So it can lead to some inefficiencies in terms of how you're tuning your topology. You might just throw a bunch of hard metal at it and not really think about, like, oh, this process really doesn't need to have a ton of memory. It's only doing CPU work. But when we put this stuff on top of Mesos, it forces us to start thinking of this and gains more efficiencies in terms of usage of the hardware. So I already kind of covered this, but basically Mesos thinks of CPU and memory. Storm doesn't. Mesos deals with allocating the CPU and memory for tasks onto hosts. Storm, again, only thinks about slots. So this is how Storm, this is like another picture of the earlier representation Brian showed of Storm, where you have a worker host, you have a supervisor, and you have different topologies that run under supervision of that single supervisor. In the Storm on Mesos model, it's actually different. So we allocate different supervisors for every topology that run on a particular host. The advantage of this is that you can isolate the topologies from one another. You can decide that this topology needs more RAM, this topology needs more CPU, and you can allocate them appropriately. And the other thing that's really important to note about something that's kind of hidden in this diagram is that these purple boxes also represent Mesos executors, which actually, if you're using C groups, are containers. So they have hard bounds on the amount of memory or CPU or other stuff as Mesos improves its resource handling. So you can avoid different topologies impacting each other. Whereas in this former model, topology C could potentially take over all the RAM on the box and squeeze out topology A and B. So that's one advantage. So this diagram is a little bit busy. What I represent is that we need to somehow map the resources that Mesos knows about into slots. And Storm has this model where it knows beforehand, I have X slots. But in the Mesos world, there's no such thing. There's not a pre-existing number of slots. We have to somehow take the existing amount of resources that have been offered up by Mesos and munge them into a set of slots for the worker processes to get scheduled onto by Storm. So this is representing how the two systems interface. They go through Java interfaces, and resources come in from Mesos, get calculated into slots, and then Storm schedules worker processes onto those slots, sending it back through the interface again into Mesos, where supervisors are created that then start worker processes. So let me talk a little bit, I'm going like too fast, I guess, but let me talk about how Groupon's Storm as a Service actually looks on top of this existing technology that is out there in the real world. So we have a dedicated Mesos cluster where we run Storm on. We created a submitter application where we can gate the topologies that are coming into our system so that we can control and kind of know who's running topologies. Eventually, we could use this to block topologies from even launching if they're going beyond certain like resource request limits. We've overcome something that I haven't touched on yet, but you might have noticed in an earlier slide here that this is a SPOF, single point of failure, the Nimbus. If it goes down, then Storm is unable to keep launching new workers, to notice that workers are down and needs to create new ones, to take in new topologies and launch them. So you have to work hard to get the Nimbus back up as soon as possible if it goes down. Storm, as Brian referenced, does store a bunch of state in Zookeeper, but it does have state that isn't in Zookeeper, such as the Storm jars themselves for your topology. So that's why it's a single point of failure right now and doesn't have HA. So that leads us to the rsyncing thing. So we rsync from our current master Nimbus onto a backup one so that we can bring up that one pretty quickly because all the state is either on that host or in Zookeeper. And we've gone through that exercise a couple of times and it works well. We've also had to create a couple of libraries to give us consistent visibility into the system to allow our users to be able to use the system nicely. So we allow you to log out into Kafka or Splunk using our libraries. We also provided a metric system so that people can get a view as to how their topology is performing, like how many tuples per second are going through different bolts, how many acts are coming back. You can also put application level metrics out into the system so that you could graph various application level interesting things for your particular topology. And we implemented this just on top of a built-in Storm thing that's not very well documented called the iMetrics consumer. Yeah. So the pros for using this system instead of using native Storm are that it provides true isolation. Storm does provide something called the isolation scheduler. However, it statically partitions the cluster. So the way it works is that you would dedicate particular worker nodes to a topology. So this topology would only ever run on those nodes. Those nodes would only ever run that topology's processes. So we didn't really like that. That's an advantage of using the Mesos-based system. It provides us flexibility for increasing or decreasing the number and size of the worker processes that you have for your Storm cluster, or topology rather, and cluster. It avoids us having a bunch of separate, underutilized clusters that everybody's having to manage themselves, look into the future and try to predict how stuff is growing and have to request from our operations team extra hosts. It reduces a lot of the burden. It also gives us some consistent visibility into the operations of our Storm clusters so that we can compare across topologies and be like, oh, well, this topology is behaving well, this one isn't. So it really is something about your topology and not the underlying system that we've built. Well, I guess I will yield the floor to AJ at this point.
All right.
I'll turn myself off.
All right. So this is a cat. We like cats at Groupon, but this is a bullet cat. We can call it a cat tuple. So the griddle part of the talk. So the griddle part of the talk is going to be focused on not just throughput, but latency. So Storm is really focused on getting the most number of tuples as you can flowing through the topology. If we go back to that Storm picture with all of those boxes, both Brian and Erik talked a lot about how a tuple will leave a machine and go somewhere else. Okay? So how about cases where latency matters and you don't want to bear the cost of serializing, deserializing network I/O? Okay? So this is called Griddle. Griddle basically gives to teams that want to use Storm a DSL which expresses with a DSP-like workflow. What I mean by that is DSP traditionally is tiny little things that you want to combine together to make this sort of gestalt behavior. They should be easier. They should be easy to mix and match. The syntax in the DSL is like a adjacency graph. Declare vertices, you declare your adjacencies. The topologies that I work with, which are specifically place data, business data, we do lots of normalization. So we're really focused on how do we get Storm to be useful for data scientists or machine learning folks. And also we talk a lot about, or I can talk a lot about mechanical sympathy, which is how about cases where you want those things to be in CPU cache. You want to run as fast as possible. Latency matters. Okay. All right. So now we'll talk about some pictures, and they're just going to be DAGs. And this is a very small portion of the place data topology. Having very complex topologies in Storm is a bit rough. It's hard to declare them. So our place topology is, I think, 20 to 30 nodes, which is a lot for Storm. It also means that you have 20 to 30 queues. Okay? All right, so let's just talk about this. So we want to normalize country code. We want to do some things with the website, postcode. This stands for out of business, not out of band. Then we geocode. So this special little blue border is indicating that this is the only node here that needs to do any I/O. Okay, so it goes out to our happy cloud, because that cloud is getting data, so it's happy. Okay, And then we want to do things with the phone numbers. All right, so this is very abstract. It doesn't really capture some really important business use cases, which are described here. Whoa. Okay, so I recognize that this picture is ugly. It's intentionally ugly because it's trying to express that in the real world, things get complicated. So what this box up here means is that we have a whole subgraph which, until we have QA'd the effect of these vertices on a country's data, that we don't actually want to run them. We would like to leave the data as it is, because we're not. So like, let's say we haven't onboarded a particular country yet. So place data we get from all over the world. And we've optimized our architecture so that we can add country by country by country. Okay? So let's say we want to add a new country. Let's say we're doing Spain, for example. And let's say these don't QA well. Okay, but we don't want to delay the business from being able to do to call businesses in Spain. So we're just going to do this part. Okay? Or it may be the case that we're starting to accept countries that we haven't even started training on. Okay, so that's fine. So they'll go through here too. All right, so go back to here. This is a really simple graph. Every vertex has an in degree of 1. Every edge is going to get walked. All right? So all of a sudden we're here. We now have vertexes that have in degree of 2, and not all vertexes are going to be walked. In fact, let's say we do want to process a country. Well, then we're going to go here, and we're going to go here. Post condition exists just to be like, yep, we did or we didn't this. Okay? If we don't want to process this because we don't like the quality of these normalizations, well, then we're going to come here. So that's interesting in the sense that those two edge sets are not disjoint. Okay. All right. So let's go ahead and maybe obviate these things to make this graph look at least a little more manageable. The first thing we're going to do is we're going to say that we have this thing called an active edge chooser. We also want to state that that means that this country code normalizer, it has no idea what vertices it's actually going to. So you decouple the behavior. This can change independently from this, so that's nice. We also now have a couple different types of vertexes, okay? So all three of these have an in degree of 2, okay? But these two are different. Because until they get data on each of their edges, they need to block, and they need to wait. So like I said, that's very different from this. There's no waiting necessary here. There's no joining. There's none of this business. All right. Okay. So this is, these kinds of joins are also very difficult in storm topologies. So now what I'd like to do is jump to what this looks like in a Griddle declaration. I'll just, the whole thing briefly, and then we're going to start to dive in. So this is a DSL, and there is a compiler. All right, so let's get started. This is a subset of the vertices that we declare. Okay, we're going to see start. Okay, very simple syntax. So this is what I was really trying to get to with, okay, A, why a DSL, and B, if you're going to do a DSL, make sure you don't force people to learn a bunch of weird random stuff. This should make a lot of sense. This is vertex, we name it, and we say what the type is. Okay? All right, so now we want to talk about adjacencies. Okay? So we're saying that we emit to postcode and website from begin country dependent. So if we go back, you could consider the conditional to be the country dependent. Here's postcode and website. Okay? All right. So these are all pretty basic. And by basic, what I mean is that we emit on every out edge. Okay? And here's a really simple little one. All right. Let's go to a complicated one. All right. So here's our active edge chooser. So this is basically saying you emit to any subset of this adjacency list from start, and you use a chooser of this type. Okay? And by any set, I literally mean any set. It can be empty as well, which could ultimately, so this is just making sure this is obvious. So let's go back to the picture again. All right. So we're saying we emit to conditional, post-conditional, or out of business from country code. Okay? But what we're doing is this active edge chooser knows, okay, we've normalized country code. What is the country? Oh, we support that one, so I'm going to go to these two. Okay? Or no, we don't support that one, so I'm going to go to these two. Okay? Country code has no idea about that edge choice. All right. Here's the picture again. I could show the cat again, too. OK. So as anytime there's a DSL, people very reasonably say, like, why do you do that? What does a DSL give you? Because it better give you something. OK? So there's a compiler, and it creates a binary graph. OK? And that binary graph is then processed by a Griddle runtime framework. OK? And the runtime framework is simply a framework. It's not a process, so that you can put it in any sort of server you want to. And that process provides optimal concurrency for the graph that you've expressed. Okay, so basically what we have now at Groupon is that for our big place topology, where we have areas of bolts that really don't need any I/O, if they were all on the same CPU, we would get a huge latency increase. We've been porting them to what we call the Griddle operator or Griddle bolt, which is a bolt running over a compiled Griddle graph and getting this really good concurrency. And we've had, empirically I should say, every time we sort of pull a bolt into a Griddle graph, we get back at least 10 milliseconds because of the queuing. So I'm not saying that's either a good or a bad thing. It's a bad thing for latency. It's something you don't really care about for throughput, right? Because if you want to say, like, we can do 10,000 a second, that means that every second you have 10,000 being processed. Okay, that doesn't say anything about how long it takes. All right, so now I'm going to cross my fingers, dive into the deep end, and I'll show you this picture that talks a little bit about the threading model. If what I say is confusing, just interrupt me. Because I really do want to motivate, like, why would we create another DSL? All right. So, good, the colors showed up kind of. OK. So this is a pretty simple graph. It's got 6 vertices. Those are blue. And you've got all your edges. And then these little red circles are basically indicating that what a Griddle graph processes is a domain value. Okay? Basically, these are unary functions. They have domain, they have range. Okay? As your domain value is moving through the graph until it gets spit out, obviously it's going to change state. Okay? So if we think of that place, like the website's going to change, geocoding is going to change, postcode's going to get normalized, things like that. Okay? All right. So here we are. The yellow boxes are vertex label and a thread indicator for what thread will be running that node. Okay? One thing I should indicate here is that I don't dive into the conditional paths. Mostly I just want to talk about the concurrency. Okay. So the green rounded rectangle is saying that there's a scheduler thread. And so what that means is that scheduling does not get in the way of any work that's already being done. Okay? All right, so we have D0. It's a pretty trivial one. It's just trying to get this graph started. Okay? So we trigger these 3 to get started. Okay? Obviously, this is handled by T0, but now we have T0, T1, T2. We have 3 threads. Okay? These emit 2 range values, and we're able to transform D0 into D1. Okay? This is one of these join vertexes. Okay? And in fact, I didn't explicate it, but within the syntax, we have this idea of aggregates inputs, okay, which means you need to wait for all of your inputs. Any vertex that doesn't have that, one input will trigger it to continue. And that becomes interesting with this one, for example. You'll notice since it doesn't have an orange box, if it gets in here, it goes to there. If it gets in here, it goes to there. Okay? All right. So we're now using T0. So now we're back down to only having 2 threads. And then we come to here, and we just have one final thread. Brian and I were talking this morning, and based on the real implementation, one could very reasonably criticize this. The fact that the T0 is running through this path is, I probably shouldn't have done, okay? Because we are not scheduling paths. We are scheduling vertices that are ready to do work, okay? So I could have just well said T0, T0, T1, T2, okay? And this is very important because what it means is that as a vertex is ready, so let's take this example. So let's say R1 takes a millisecond, but R2 takes 10 milliseconds. I don't know. Actually, I hope it doesn't, because that doesn't sound very good latency. So as soon as this is then ready, it's going to come up and be scheduled, because it says, I'm ready to do some work. So that ability of being ready isn't related to the particular path. It's related to the state of the vertex. All right. Questions?